Hello everyone, Aaron here. We're back on Leetcode, and today we are looking at search in a binary search tree. Now, binary search trees are basically defined as that the left thing is going to have everything that's smaller than the node, and everything on the right, and the right child is going to have everything larger than the current node we're looking at. So here, the 4, every part of its child, 1, 2, 3 is smaller than 4, and on the right, 7 is larger. Same thing happens recursively. 2, everything smaller is on the left, and everything larger is on the right. This is kind of one of those standard coding problems that you'll have to come across at one point or another. So definitely really good to manage the basics on this. Should be a short and sweet video if I don't completely fuck it up. Right. So we are given the root of a binary search tree and an integer val. Find the node in the BST that node's value equals val, and return the subtree rooted with that node. If such a node does not exist, return null. So if we're looking for 2, we're not just going to return the 2, we're going to return the entire subtree attached to that 2. They've given us the definition of the binary node here. So fairly straightforward. If root val is equal to the value we're looking for, return to root. Otherwise, what are we doing? In fact, we've got another condition at the beginning. If the root is nothing, return null. So the case here that we're looking at, if the root is null, we've somehow descended into a branch that didn't exist, in which case we're never going to find the thing we're looking for. So that's this null case here and this null case here. This case here is we've found what we're looking for, and effectively those are our two base cases. This is going to be a recursive solution. Trees are a recursive data structure, so recursive algorithms tend to match them very, very naturally. So, base cases, recursive case now. If the value that we're looking at is less than the value of the node that we're currently at, we want to return the search BST of root.left. Remember, we said everything that is smaller is on the left. So the value we're searching for, if it exists anywhere, is going to be on the left-hand side. Otherwise, we're obviously going down the right-hand side. That doesn't line up. Oh, I've got 2 E's. That's not what we're after. Honky dory. Short and sweet one, this. Let's see if let's do a quick run through in our heads, see if it works. Search BST, root, tree node, null. That's the whole thing. If the root is nothing, if the root is null, return null. We were unable to find something. If the root is what we're looking for, return the root. Otherwise, we want to descend either left or right, depending on whether it's smaller or greater. I propose we just run this thing, see what happens. Not bad, that seems to work fine. Let's submit it. Let it run completely. Finished. Ran 110 milliseconds faster than 68.53% TypeScript solutions. Use that. I reckon we can probably do a bit better. Let's see if we can do it non-recursively. And I think the way we want to do this is effectively remove the recursion and turn it into a while loop. Let the current thing we're looking at be the root. And while the root does not equal null. So as soon as the root is equal to null, we'll just return null. But then all of this condition in here, we're going to move that in here and have a bit of a futz around with it. Ugh. One problem with Leetcode is editor is meh at best. If the root value equals so this condition is the same. If we're where we're looking for, we are done. If the value is less, rather than recurse into the new thing, we want recurse. It reminds me, I'm looking at the current thing the whole way here. Not the root, just the cur. And same conditions, but rather than doing a recursive call, all we're going to be doing is updating the thing we're focusing on. I called it curve for current. So if the thing we're looking at is null, bail out, end. If the thing we're looking at is correct, great, we'll go from there. We're done, return it. Otherwise, move left to right. So we were looking at 110 milliseconds, 49.9 megabytes. Let's see if we can cut either of those down a wee bit here. Quickly do a little test, just to make sure I haven't got any of my syntax wrong. I think we're good. Let's see what happens. Excellent. We took the tiny little bit of the memory requirements. That's neither here nor there, but the runtime is way down, and we're now in the top 7% of runtimes. Perfect. This is obviously a bit less clean, a bit more familiar if you're used to the imperative programming, but it doesn't mirror the structure of the data type quite so tightly, whereas the recursive solution is basically follows the definition of the data type. Well, I think that'll do it for today. Short and sweet one today. Thank you very much for watching, and I will see you tomorrow. Bye.